An electromagnet is a temporary magnet which attains magnetic property when current flows into the coil of insulated copper wire wound around a soft iron piece. Electromagnets are generally made into two shapes: bar or I-shaped magnet and horseshoe or U-shaped magnet. For making a bar or I-shaped electromagnet, take a soft iron bar PQ and wind a thin insulated copper wire around this bar. Now connect the two ends of the wire with the help of a battery and attach a switch or key in series with the battery. Now when the switch is pressed, means this whole circuit gets completed. Then the current starts flowing into the coil and this bar PQ will start behaving as a magnet, means it will attract small pieces of iron. As soon as the current stops flowing into the coil, this bar loses its magnetic properties and again starts behaving as a normal iron bar. So, this bar PQ will behave like a magnet when the current will flow into the coil. Thus, this is an electromagnet which is bar shaped or I shaped. To make a U-shaped or horseshoe electromagnet, take a U-shaped soft iron piece. Now wind a thin insulated copper wire on the arms of this iron piece. We have to keep in mind that this winding should be done in such a way that on both the arms the wire should be wound in opposite direction. Means if the winding on arm A of the iron piece is done in clockwise direction, then on arm B it should be done in anti-clockwise direction. Now both the ends of the wire are connected with a battery and a key. When the key is closed, the current starts flowing into the coil and it will start behaving like a magnet. The magnetic field will be produced between the two arms of the iron piece and this will work as an electromagnet. Now when the key is open, means the current is stops flowing. Now the current is not flowing into the coil, then this electromagnet loses its magnetism and again start behaving as a normal iron piece. Thus we get a horseshoe or U-shaped electromagnet which works like a magnet when the current flows into the coil. The electromagnets are mainly used for the following purposes: for loading furnaces with iron. So if we have to load furnace with iron, then we use electromagnet as it attracts iron when the current is flowing in it. Now when we have to drop those iron pieces in the furnace, the current is switched off. As soon as the current is switched off, that electromagnet starts behaving as a normal iron piece and drop all the iron pieces which were previously attracted with that magnet. So this way we use electromagnets to load furnaces with iron. For removing iron dust from the wounds, we use electromagnets. So if we have to remove iron dust, any iron particle from the wounds, then also electromagnets are used. If we have to separate magnetic substances from other non-magnetic substances, if all are mixed together, then we can easily separate the magnetic substances using electromagnet. To lift or transport big pieces of iron, then like iron girders or plates, if we have to lift and transport from one place to another, then also we use electromagnets. In many electrical gadgets like electric bell, electric motor, microphone, etc., we use electromagnets. One of the most common application of an electromagnet is an electric bell. An electric bell consists of a horseshoe electromagnet, a soft iron armature, a hammer, a gong, a metallic springy strip, an adjusting screw, a switch or bell push, and a battery. Now you can see in the given figure, armature is connected with a metallic springy strip. Another end of the armature is attached with a hammer. The metallic springy strip is in contact with the adjusting screw. When you can see when the switch is off, it is not pressed. Till then, adjusting screw and metallic springy strip both remains in contact with each other. A U-shaped soft iron piece is placed and a coil is wound on it. Now the winding is done in such a way that on both the arms winding is in opposite direction. Means if on one arm winding is done in clockwise direction, then on the other arm it is in anti-clockwise direction. One end of this coil is connected with terminal T2. Another end of the coil is connected with metallic springy strip. This metallic springy strip is then connected with adjusting screw, which is connected with terminal T1 with the help of the wire. So both the ends of the coil, this coil you can see wire is wrapped around it. So both the ends are connected with terminal T1 and T2. Now between these two terminals, a battery and a switch is placed in series. So switch and battery are joined with terminal T1 and T2. So this is the whole construction of an electric bell. As you can see, when the switch is not pressed, then the adjusting screw and the metallic strip remains in contact with each other. When the switch is pressed, the circuit gets completed and current starts flowing through the coil, due to which the U-shaped iron piece becomes an electromagnet, which attracts the armature. When armature gets attracted towards the electromagnet, then the hammer attached with the armature strikes the gong, due to which the bell rings. But because of the movement of the armature, the connection between the adjusting screw and metallic strip breaks, which makes the circuit incomplete, so current stops flowing. Now the electromagnet loses its magnetism. The armature then returns back to its initial position, due to which the metallic strip again comes in contact with the adjusting screw. Now the circuit gets completed, and when switch is pressed again, the same process gets repeated and the bell produces sound. We know that Earth itself behaves like a huge magnet, due to which a freely suspended magnet rests in north-south direction. The magnetic south pole of the Earth is towards geographic north, and magnetic north pole of the Earth is towards geographic south. We know unlike poles attract each other. So, when a magnet is suspended freely, then north pole of the suspended magnet gets attracted towards the magnetic south pole of the earth, which is towards the geographic north, and south pole of the suspended magnet gets attracted towards the magnetic north pole of the earth, which is towards geographic south. But the suspended magnet do not rest exactly on geographic north and south. It is slightly away from geographic north and south. So the angle between the geographic north and magnetic north of the suspended magnet is called as the magnetic declination. It is represented by symbol theta. Now this angle changes with change in place. If the magnetic north of the magnet, that suspended magnet, is towards the east of the geographic north, as you can see in this diagram, it is towards east of the north, this side, then declination is taken as positive. But if it is towards the west, means the suspended magnet is resting in the west side of the true north or the geographic north, then the declination is taken as negative.